Hi, and welcome to the next lecture in aerodynamics. Today we will be continuing our exploration of supersonic shock wave flows. Last time, we discussed normal shocks, a special case of shock wave where the flow direction is perpendicular to the shock itself. We developed equations that describe the flow condition downstream of the shock from upstream known conditions. The shock causes the flow to jump in condition, lowering the speed but dramatically increasing pressure and temperature. We also defined two special flow conditions: stagnation, which is the case when flow velocity is brought to zero, and sonic, where flow velocity is brought to the speed of sound. Today, we'll be looking more at applied shocks. Oblique shocks occur when a surface closes in on a flow and produces an angled shock wave. Expansion fans are quite different and occur when a surface opens, but instead of a discontinuous jump, there is more of a continuous series of small shocks that change the flow behavior. Additionally, we will consider the special forces produced by these types of flows, specifically the wave drag. Let's jump right in and continue our exploration of shock waves. We start by considering and deriving the behavior downstream of an oblique shock. An oblique shock is created by a surface that is angled inwards into the flow near a supersonic flow field. This type of angle is characteristic of converging flows, and you often see them at the leading edge of wedges or in contractions. Unlike a normal shock, flow comes into an oblique shock at an angle. The shock itself has an angle beta, and as flow passes through the shock, it changes direction slightly and deflects at angle theta. Things are 2D now, and now we have two velocity components to consider, with velocity vectors changing direction. Now it's fair to ask why the shock occurs at a certain angle and not necessarily just normal to the flow. Consider a moving sound source like a bell. As the bell rings, it emits pressure or sound waves outward from the source. The bell is moving to the left at velocity u, and the sound waves emit from the bell at sound velocity a. If u is less than a, the bell stays within the sound waves, and this is representative of subsonic flow. Now, consider if the bell were moving at a speed faster than the speed of sound. The bell would still emit sound waves, but it would constantly outrun that sound wave and exist outside of it. The edges of sound waves coalesce into an angled wall, where we'll label the angle as mu. This angle mu is called the Mach angle and is a direct function of the Mach number coming in. Note here that the Mach angle is really the lower limit for angled shocks and is specific to very weak disturbances. In reality, the oblique shocks have a slightly larger angle. Consider supersonic flow past a wedge. The oblique shock angle is called beta and is necessarily larger than or equal to the Mach angle. Luckily, oblique shocks behave identically to normal shocks, so we can use everything we've learned in the last lesson. However, for an oblique shock, only the velocity component normal to the shock is impacted by the shock itself. We will denote normal velocity components with the subscript n. Let's sketch an angled shock wave. We have an incoming velocity that's supersonic, denoted as m1. This velocity vector has a component normal to the shock, which we will call u1, and tangential to the shock, which is v1. The normal component also has a normal Mach number. After flow passes through the shock that has an angle beta, it is deflected by the angle theta, and there is a new normal and tangential component. The tangential component is unchanged through the shock, so v1 equals v2. Conversely, the normal component is slowed by the shock, so u2 is less than u1, which also means that the normal Mach number is less. The fact that the normal component changes while the tangential component is unchanged means that the velocity vector is deflected, in this case upwards. The flow that passes through normal to the oblique shock follows the normal shock equations. Let's write out the equations for an oblique shock using what we know about normal shocks in trigonometry. First, let's define the normal Mach component based on beta. From the normal shock equations, we can define the normal Mach number after the shock as a function of the normal Mach number upstream. Then, we can use trigonometry again to get the eventual downstream Mach number. And we can define the density, pressure, and temperature ratios based upon the upstream normal Mach component. But now we have these new angles, beta and theta, to worry about. Let's try to find the theta angle as a function of beta and the upstream Mach number. Keep in mind, beta is the angle of the shock and theta is the deflected angle of the velocity. Using trigonometry, we can relate the two angles to their respective velocity ratios. Also, we will keep in mind that the tangential velocity components on both sides of the shock are equal. If we rearrange these equations so that we get a ratio of the normal velocity components, we can redefine it as the density ratio from the normal shock relations. This we can define as a more complex ratio of the normal upstream Mach number, and then using our trig relation, we can define it as a function of the Mach number and the beta angle. Rearrange this to solve for theta, which can be solved for with only the shock angle and Mach number upstream. This is called the theta-beta Mach relation. In reality, you typically know theta ahead of time because it is the angle of the body moving through the gas. For a wedge, this is the wedge half angle. And you tend to know the geometry of your body in your problem. You also tend to know the upstream Mach number because that's the speed of your body moving through the gas. In practice, the theta-beta Mach relation is used as a lookup chart, where you find the beta angle on the chart that corresponds to your theta and Mach number. The chart you use would look a bit like this, where different Mach numbers are plotted comparing the deflection and shock angle. You pick up the chart, find your theta angle and Mach curve, then find the corresponding beta solutions for that angle. There are a few important features of this plot to point out. First, nearly every Mach number theta angle combination yields two solutions for the shock angle beta. The lower of the two is the weak angle, and the larger of the two is the strong angle. Technically, reality can choose either of these two angles because they satisfy the relation, and depending on the size of the disturbance, it can change. However, more often than not, the weaker shock wins out. Second, you might notice from the chart that every Mach number has a maximum theta angle or a peak. This poses a problem if the body generating the shock has an angle larger than this maximum theta. And when this occurs, you get a detached shock. Consider a thin wedge in a supersonic flow. When the body angle is less than theta max, it is a typical attached oblique shock. However, when the wedge angle is larger than theta max, the shock detaches and curves, creating a bow or detached shock. All of this depends on your body's speed and geometry. Much like normal shocks, we have the capability to calculate the downstream condition past an oblique shock from the input Mach number with the new nuance of the shock and deflection angles that can be explored with a lookup table. But what happens in the opposite case when the flow opens? These are called expansion waves or expansion fans, and they're very different from oblique shocks. Expansion fans occur when you have an angled surface in a supersonic flow that opens or diverges. Flow bends around the corner through the fan, and like an oblique shock, it deflects. However, the expansion fan has a thickness to it. Normal and oblique shocks were characterized as having a super fast jump in flow condition, and at such a fast jump it is considered relatively discontinuous and instantaneous. So, we analyzed it with a control volume method and we were just concerned ourselves with what went in versus what went out. However, fans are inherently different. The change to the flow is more continuous, or gradual, and the change to the flow is also isentropic. Being continuous is important because it allows us to analyze the flow with calculus, like derivatives and integrals. Moving forward, we will treat expansion fans differently to normal and oblique shocks. I want to note here that, unlike oblique and a normal shock, expansion fans can cause the flow to accelerate. This means that the downstream Mach number is often larger than the upstream Mach number. This type of behavior is almost exactly the opposite in subsonic flows. In a subsonic flow, when it passes through a converging region, it tends to accelerate, and when it diverges, it decelerates. However, in supersonic flows, converging often means deceleration, and diverging means acceleration. This is an important concept for supersonic wind tunnels with converging-diverging nozzles, and also for propulsion systems. But those are for another course. Okay, back to the calculus. We're going to consider infinitely small changes happening to the flow as it passes through the fan. Let's consider an expansion fan and zoom in on one single shock that exists in the series of shocks that make up the fan. As flow with velocity vector u passes through the shock, it deflects slightly by angle d theta and changes velocity slightly by du. Let's call the angle of the shock here mu, much like the Mach angle from earlier in this video. And also, for convenience, we will define some of the opposite facing angles where the angle opposite the velocity vector and the shock is pi over 2 minus mu minus d theta, and the angle opposite the shock itself is pi over 2 minus mu. To start our analysis, we need to do some heavy trigonometry, reorganization, and simplification. If you get lost, it's okay because we aren't making any physical arguments here, just applying trigonometry. We'll get through it pretty quickly. Our end goal is to define the velocity and its differential by a simple functional form of mu and d theta. First, we recognize that the ratio of the two velocities up and downstream of the shock is equal to the ratio of these opposite angles we've just defined. Let's apply an identity to the signs, where sine of pi over 2 plus mu becomes cos mu, and sine of pi over 2 minus mu minus d theta becomes cos mu cos d theta minus sine mu sine d theta. Plug these relations back into the original top equation. D theta by definition is small because it's an infinitesimal change in theta. So, we can make use of the small angle approximation and cos d theta becomes 1 and sine d theta becomes just d theta. Follow these assumptions through and we arrive at something relatively simple, 1 over 1 minus d theta tan mu. This is where we stop with trigonometry, but we can make a few more simplifications if we recognize that this looks something like 1 over 1 minus x. And we can consider the Taylor series expansion of that term. This expands to 1 plus x squared plus x cubed, and it goes on. Let's replace x with d theta tan mu and see what that gets us. We're going to keep the first two terms and ignore everything else because d theta squared and higher are terms that are super small. What we're left with is a fairly simple relationship between du over u and d theta and mu. Rearrange this so we can isolate d theta. And lastly, we can apply our definition for the Mach angle mu that we had from above. Solving this out and simplifying for d theta gives us the following expression that describes the small change in deflection angle as a function of the incoming Mach number and small change in velocity. And as we've done many times before, let's recognize that we don't necessarily care about a single small change, but what happens when we add all the changes together into the actual expansion fan. To do this, we need to add up all our small changes through integration. On the left, we integrate from 0 to theta, and on the right we integrate from the starting and ending Mach numbers after passing through the fan. Let's quickly redefine the u's as Mach numbers using compressible flow relations. Plug this back in and we get an integral that contains just Mach number as a variable. This integral is going to be defined as a function to make things easier down the road. This nu is a function of Mach number only. Let's do out this integral in its entirety and we get a rather long expression for nu. This function, nu, is called the Prandtl-Meyer function. This means that in order to get theta, we evaluate this function at the downstream Mach number and the upstream Mach number and take the difference. Like many other things in supersonic flow, this relationship is usually interacted with as a lookup table in a reference, although direct calculation is possible. You might look at this and ask yourself, how do you use all this? Well, let's consider a realistic scenario where you know the incoming Mach number, which is based on the velocity of your aircraft or incoming flow, and the theta angle, which is typically a function of your body geometry. Knowing both of these things is common in application. From the incoming Mach number, you can obtain a Prandtl-Meyer function value using a lookup table or through calculation. Then, using that value and the known theta, you can find the Prandtl-Meyer function value of the downstream Mach number. And through a lookup table or direct calculation, you can then find what Mach number downstream you would need to get that Prandtl-Meyer function value. And once you know the downstream Mach number, you can also start to explore the other downstream flow conditions like the super important temperature or pressure downstream. We'll have to do a little bit more derivation to get expressions for the downstream pressure and temperature, and we need to take advantage of our isentropic nature of the fan. If flow is isentropic, the stagnation properties are unchanging. This means that the stagnation pressure and temperature at any 2 points are equal. If we take the pressure ratio, P2 over P1, we can multiply by the stagnation pressure, which is effectively 1. We can treat the temperature similarly. Recall from our past studies the relationship between stagnation temperature and pressure as functions of local Mach number. Combining these relationships with the ratios above, we can define new equations for the ratio of pressure at 2 points and temperature at 2 points as functions of the two Mach numbers. These two relationships are how you get the downstream pressure, P2, and temperature, T2, for an expansion fan. Let's zoom out and think about how far we've come along. For normal shocks, for oblique shocks, and for expansion fans, we have upstream and downstream conditions labeled here 1 and 2. Using the relationships we've derived in the past 2 videos, we can now completely describe the downstream conditions using upstream values and gas constants alone. All you need to know is what type of shock you're dealing with, which is generally dependent on the geometry, and how fast you're going. To finish, let's also consider the lift and drag produced by these flows, because knowing body forces is very important for knowing if you stay in the air and how much thrust you need to keep your velocity. This is something called shock expansion theory. We can't go into detail on it, but you can use this technique to find the forces on complex shapes due to the presence of shocks and expansions. Let's consider a supersonic angled flat plate as a simple example. At the leading edge of the plate, at the top, the flow opens or diverges, so we get an accelerated flow and an expansion fan. On the bottom at the leading edge, we have a closing flow, so an oblique shock that slows things down. The exact opposite happens at the trailing edge, so that the flow reverses back to the normal condition. We can think of this flow as having 4 distinct regions. The incoming and outgoing flow are region 1 and 4, the flow on the top of the plate is region 2, and on the bottom of the plate is region 3. In region 2, the pressure is lower than the incoming pressure due to the passing through the fan and flow acceleration. In region 3, the pressure is larger than the incoming pressure because the flow is passed through an oblique shock and is slowed down. This pressure difference across the plate leads to a body force, N, which means there is a lift and drag on the plate. The drag on the plate is a new pressure drag that does not exist in subsonic flows, and this is called the wave drag. In some cases, wave drag is avoided, as in commercial flights where the flight speed is specifically set to avoid shocks in this wave drag. So, by understanding the behavior of all these shocks, we can also understand the body forces they produce. Let's end on a practical note. In aerodynamics, you come across oblique shocks and expansion fans all the time when working with supersonic flows. You see them in explosions, in ballistics and munitions. You obviously see them in aircraft, and they're quite commonly utilized in propulsion systems like scramjets. Additionally, the equations we've developed over this in the past video are used to dictate aircraft shape and design. It's what motivates the sharp edges on these types of crafts. Material choice to deal with the super high temperatures that come with supersonic flows. And the forces and moments on the body, which are altered by these shocks through things like wave drag. Let's review what we've done today. We started by jumping straight into oblique shocks, which behave identically to normal shocks. However, we need to consider the shock angle and deflection angle due to the flow passing through the shock at a non-normal angle, which is done through lookup tables and charts. Expansion fans were quite different, which have a thickness and produce a more gradual flow change. Through calculus, we were able to derive the Prandtl-Meyer function, which allows us to procedurally find the downstream Mach number from the upstream condition in geometry alone. We ended by considering the forces on a body and by introducing the shock expansion theory. This brought to light things like wave drag, which can be detrimental to aircraft performance. In practice, these equations and relationships we've derived in the past two videos are everywhere in supersonic flows. I hope you enjoyed the video, and thanks for watching.